Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back again to this online structural geology NPTEL. Today we are in our lecture number 14 and we are learning deformation mechanism of rocks. So in the previous lecture we learnt about different types of crystal defects, and today we will mostly focus on cataclastic deformation, which generally happens at the surface or shallow part of the earth. And we will follow in the next lectures with intercrystalline plasticity and then mechanisms of recrystallization with examples from deformed quartz. Now this lecture, as I said at the very beginning, we will classify the deformation mechanisms, and then we will mostly spend the entire time on discussing the different processes of cataclastic deformation or brittle deformation. Mostly we will focus in the micro scale processes or grain scale processes. So before we jump into the actual processes and classifications, let us have some basics. We have learnt about it. So deformation of rocks, as I told in the last lecture, is achieved by various processes, and it is now quite obvious and well established that does not matter how large is the scale of the deformation, deformation do initiate at a very small scale in the crystal scale. So a large fault, if you consider, it initiates with a very tiny fracture or number of tiny fractures. So either the tiny fracture propagates in response to the stress, or lot of tiny fractures they coalesce and then propagate together to give rise the large scale faults. So now all these processes, at least today we will learn the cataclastic processes. So this is mostly achieved by different processes, and these processes are functions of majorly two parameters. One is the lithological controls, or sometimes we call it intrinsic parameters. So if I write it like this, intrinsic parameter, and then another is external control. So that is known as extrinsic. Now within the intrinsic or lithological controls, you may think of the parameters which are inherent of the rock. So that is mineralogy, you can think of composition of the fluid that you have in the rock, or the different grain sizes, crystal orientations, porosity, permeability, etc., etc. On the other hand, external controls are the ambience where the rock is being deformed. So there you can think of pressure, temperature, pore fluid pressure, the rate of deformation or strain rate, etc., etc. Now while these processes are these parameters are controlling the deformation processes, and while the deformation do happen under different controls, then they produce characteristic microstructures and submicroscopic features. What I mean by that a brittle rock or a rock that has undergone brittle deformation would have a very typical microstructure to that of a rock has undergone a ductile deformation. And this you probably have seen in thin sections if you have at all studied this. We will learn more about it in the next lecture. We will have some photograph of thin sections in this lecture as well, particularly relevant for brittle deformations. But the point is, looking at the microstructures, you can certainly figure out that the mechanisms or processes of deformation were different at different regimes, if you consider whether this was brittle or ductile. Now based on that, people do study deformation mechanism of rocks primarily to understand or establish the ambience, and at the same time different internal controls. So, it could be the grain size or mineralogy and so on. So, we generally get all these information through experiments, and then we match it with the natural deformation, natural deformed rocks. So, we vary pressures, we vary temperatures, we change the composition of different fluids, we deform the rocks at various times, etc., etc. So, we do all these sort of things, and then we plot them in different ways. Maybe it is stress versus strain, maybe it strain rate versus stress, peak stress versus strain, and with the control of pressure, temperatures and so on. We have seen this in one of the last lectures, and then out of these curves we infer different parameters, rheological parameters, and based on these rheological parameters we find the constants. So, the final aim is to figure out that what could be the flow law, that what sort of rheological law is applicable to this kind of studies, and therefore, we theorize it by experiments, and then the people who do numerical modeling or even analytical modeling, they use these sort of parameters or some basic equations to fit in their large scale numerical model and get the bigger picture. So, this is how the different disciplines of structural geology, if we can think of different ways of looking at structural geology. Someone goes to the field, collects rocks in sections, then someone does experiments, and someone does numerical modeling, and as a whole we get a comprehensive idea of the entire process. So, if we try to classify our deformation mechanism that we are talking about, then there are three major categories or three major classes of deformation mechanism, and this is mostly derived by observing naturally and experimentally deformed rocks. The first one is cataclastic deformation, second one is intracrystalline plasticity, and the third one is diffusive mass transfer. As the name suggests, you can figure out that cataclastic deformation is mostly considers brittle deformation, where rocks do fracture. The intracrystalline plasticity is something where we consider the deformation of grains, and this deformation of grains do happen at high pressure and particularly at high temperature, where all these defects that we have learned in the previous lecture do influence or do govern the deformation. So, it is a deformation within the crystal. So, please remember this term, it is intracrystalline, not intercrystalline. And then of course, diffusion is one of the very important processes of deformation, and we will learn about it in our lecture number 14.3. So, today we will mostly focus on cataclastic deformation, and as I said in the previous slide, that each of these, be it cataclastic, be it intercrystalline, be it diffusive mass transfer, if you look the microstructure, they are characteristics for each and every processes. So, they produce different types of fabrics, different types of appearance of the rock under thin sections and so on, and people do study it not only under optical microscopes, but electron microscopes, particularly scanning electron microscopes and transmission electron microscopes are nowadays very useful, and in recent days there are some other tools that you can use, even go check the atomic scale processes using atom probe tomography and so on. So, again the primary aim of studying these three mechanisms is to figure out the different relationships between stress, strain and other parameters, that how they are related and how we can put them together in different flow laws. So, let us start with a cataclastic deformation mechanism, and we will first learn that what are the characteristics of cataclastic deformation. So, I have given a list here in this slide. Cataclastic deformation is nothing but when your grains do fracture or you have some sort of frictional sliding of the grains. So, it is a combination of brittle fracturing and frictional sliding of grains, and if you have to fracture or frictionally slide the grains from one pass to another, then it is activated only when you exceed the shear strength of the rock or shear strength between the two grains. We will learn about it later. Brittle deformation or cataclastic deformation, as we have learned, that it has to be a low temperature process. Therefore, we mostly see this either on the shallow crust or on the surface. As I said, that there is no internal distortion of the crystal or lattice structures during cataclastic deformation. So, crystal defects hardly play any role in cataclastic deformation. Grains just do fracture, they rotate, they break, they just slip past each other, but internally the crystals do not show any special type of deformation. If that happens, then it is intracrystalline plasticity. We will learn about it in the next lecture. The deformation is not that temperature sensitive, as I talked about in this point, that it is a mechanism of low temperature, but pressure do play all sorts of pressures. You can think of the confining pressure, you can think of the pore fluid pressures. They do play a very important role in controlling the different processes of deformation mechanism under cataclastic deformation. If you recall, we have learned that the strength of the rocks do vary greatly when we vary the pressure and pore fluid pressure. So, as I said, that this is pressure sensitive and at the same time it is low temperature deformation. So, we commonly observe at the upper crust or on the surface or at the shallow surface of the earth, and essentially it is characterized by fracturing at any scale, but today we will mostly look at the fracturing at grain scale. Now, we can classify the entire range of cataclastic deformation in three basic ways. The first one is localized deformation, sometimes we call it frictional flow with special characteristics. Second one is granular flow, and third one is cataclastic flow. So, in the entire lecture actually we look at these three basic processes of cataclastic deformation. As you can see, it is not a typical flow, but rock do deform, they move from one point to another point. Therefore, I use this word flow here, but within inverted commas. So, let us look at the first process, which is localized cataclastic deformation. Generally, the characteristics of this localized cataclastic deformation includes extreme fracturing and grain size reduction along a narrow zones. So, so it is extreme fracturing and grain size reduction along narrow zones, and when I talk about narrow, it is millimeter to centimeter scale. Now, this fracturing or grain size reduction may happen by compaction or may happen by shearing. So, sometimes the nature of contact between the two surfaces, which we will learn later, is called asperities. If that type of flow do happen, that means one is sliding past another in grain scale, then sometimes we call them as frictional flow. Now, clearly if you increase the sliding velocity or if you increase the strain rate, that decreases the frictional resistance. So, therefore, sliding velocity or the force, if you have more, then you quickly deform the rock. And as an example of localized deformation, you can cite many. So, compaction bands are there, shear fractures are there, and sometimes cataclastic bands are also included in the localized type of cataclastic deformation. We will learn all about this in the following slides. So, here are some examples that of cataclastic deformation in the field. So, in both examples, this one and this one, the host rock or the country rock is sandstone. This I have taken from a very recent publication from Ballas, 2015. And what we see here, we have learned the conjugate shear fractures, if you remember. So, we see that two sets of fantastic conjugate shear fractures are there, and these are known as compaction or cataclastic bands. So, we will see the microstructure of this soon, and in this case as well you can see that dominantly one set is there going like this, and at the same time we have one very weakly developed another set, but it is at an angle with the previous one. So, these are the look of deformation bands or cataclastic bands or localized bands, localized cataclastic bands in the field. This is how they look like, and I am sure you have seen it when you go to the field, particularly in sandstone rich terrains which are deformed a while. Now, you also can see that these shear bands or cataclastic bands also displaced by the next generation of fractures. So, we will see that these are what are the grain scale processes of this in some of the following slides. Now, this is how it looks like when we see them under microscope. The first one is an optical microscope image. So, you can see that these yellow things are your sand size grains, and then the background is blue colored, these are your porosities, and you clearly see that there is a zone at the middle running from west to east where there is an anomaly. So, this part is little heterogeneous compared to this area and this area. What we see here, apparently if we measure statistically, the grain sizes here are little reduced from what we see outside, and at the same time the porosity has also reduced, and the number of small or finer grains along this narrow zone is quite significant, and as I said, this length is about 1 millimeter. So, we are looking at this about 1 millimeter scale. So, this is a very narrow or thin zone. We can also see the second image. This is a scanning electron microscope image, that is why it is in grayscale. What we see here more or less very similar feature. We have larger grains outside, these are sand sized grains, and then we have this. So, what we see here, this dark gray grains are sand sized grains, and then the lighter gray are the cements which filled the matrix. Now, again we see in the middle running from west to east this zone here. Here it is again little anomalous with respect to the top and bottom of this image, and the grain sizes here got reduced, sort of we can think they got pulverized and compacted together. The cements are almost absent in this area. We also see a very typical fracture or opening here along this. So, these are all characteristics of localized cataclastic deformation that happens at a very narrow zone here and here, where the grains do compact or they move past each other by producing some fractures within the grains, and they just compact together. So, if we try to figure out the different processes, that how does it happen, here is an illustration of the different processes that we can think of. I have given 4 illustrations here, and this is mostly applicable for frictional flow. So, in the first image, which is A, what we see here, that we have an arrangement of grains with some porosities which are white here, and then these red areas are some tiny little fractures that developed due to application of some sort of deformation. So, you can think of maybe deformation is going on this way, and now these little red lines they can connect to each other as I was talking about, and they can produce a continuous fracture. Okay. Now, these continuous fracture does act as an weak zone. So, if the shear continues, then these along these fractures, these two blocks are separated now, and they try to slide past each other. Now, what we see here, now because of this red area, red line here is not very straight. So, you can clearly see that if I try to draw it here, this is a fracture, and I have some grain here and I have some grains here. So, now if this one moves in this side, so clearly you should have an opening here like that, and then it tries to coalesce here this way. So, you generate an enormous force here. So, the grains here do fracture, and this is exactly what is happening here. This area along this narrow zone, we are producing lot of fractures, particularly on the contact zones. So, we have a rough surface defined by very tiny fracture which is continuous, and this rough surface, this roughness is known as asperity, as we talked about in the other lecture, as we talked about in the other slide, as we talked about in the previous slide. So, once this starts further moving, then these fractured grains, it is much easier to deform it, and therefore, you eventually end up with a very narrow zone where your grain sizes got significantly reduced, the porosities as well. So, this is how the localized cataclastic deformation is achieved, particularly in the context of frictional flow. Now, let us have a look of some more natural examples, that why we should be concerned, or why should concern about this kind of narrow localized brittle or cataclastic deformation. What we see here, this is a field photograph, and this is a thin section of the same area. Now, we will see that this is about 1 millimeter later in the later image. So, what we see here, you can clearly see very nicely, the photograph is taken by Professor Foyson. You see, these are the little grains here, and then along this narrow zone we have something got really crushed, just sort of pulverized here. Okay. And the thin sections also are revealing the same feature. So, now here we can see the individual grains separately, the blue areas are your porosities, the open spaces, but along this zone you can clearly see that within these zones the grains are crushed, they are highly pulverized, grain size got reduced, and porosity also is extremely less. This is a very interesting area where you can see that probably it was like this, it just got cut from here because of the shearing deformation. And again, this is a very narrow area, very narrow zone along which the entire deformation is accumulated. The rest of the area of this section is virtually undeformed and not affected by the deformation at all. But we still have to answer the question why we should be concerned about this kind of deformation. So far we have seen that whatever examples we looked at, that along this localized cataclastic deformation bands, the porosity got reduced. Can we have an example otherwise, that is whether we can see that no, the porosity also can increase along this deformation bands, and the answer is yes. So, this image is exactly what we have seen in the previous slide. So, where we have seen that porosity got extremely reduced here along this narrow zone. However, in this exposure here the rocks are little compacted compared to this, but this deformation band that we see here, here you can see a large openings, right, at least from the field photograph we see. So, we hardly see these openings outside. Therefore, here we can conclude that in this image we got porosity reduced, and in this image along this localized cataclastic band we have porosity increased. Now, if porosity increases, therefore, the permeability also do increase. So, the take home message from this slide is that you may have a porous rock which you may consider that okay, this is a good permeable rock, but if this rock has cataclastic localized deformation bands which are compacted like this, then your flow or permeability would be significantly reduced even if the host rock is extremely porous and permeable. On the other hand, these narrow channels in this image could be an excellent avenue for flowing the fluid even if the rock is compact. So, based on that we will see later that what are the different ways we can classify this localized deformation bands, but before that we focus on the granular flow of the cataclastic deformation. So, granular flow, unlike the cataclastic localized deformation bands, are characterized by rolling and sliding of rigid particles past one another. We will see the examples soon, and this is a very interesting type of deformation mechanism under the cataclastic domain. We mostly see these sort of deformations in unlithified sedimentary rocks, where the confinement is extremely low. What I mean by extremely low or low confining pressure, low effective confining pressure, we will understand, we will see the examples. However, it can also happen at great depth, where the effective pressure is also reduced if we have a good number of or good volume of partial melt in the system. So, therefore, as we have learnt in one of the previous lectures, that if we have pore pressure significant compared to that of the confining pressure, then your effective confining pressure reduces. So, therefore, you see or you can consider this as very low effective confining pressure, and that can happen when you have a rock with partially molten features. But these are very rare, and we will not explore this particular feature in this lecture. And this type of granular flow that we are talking about under the cataclastic deformation are described, or example you can think of are debris flow, movement of landslides, alluvial fan, rolling of beach sands, etc., etc. We will see these examples, but first have a look how does it work. So, in a very similar illustration I tried to show you how does it work. So, this is illustration A, where the grains are under low confinement, they are not compacted, so they are not lithified, and they are embedded with unlithified, also unlithified fine grained sediments or water rich sediments, which are the little dots. As you can see that grains are, because they are not lithified, they have ample spaces between the grains. So, if a deformation is being applied and the overall confinement is very low, what happens, these fluids or these fine particles or fine sediments, fine matrix, they try to flow around the grains, and when that happens, then the individual grains, as you can see here indicated by black circular arrows, the grains tend to rotate. Now, when they rotate, now when these grains do rotate, of course, they collide each other along a certain point, and when this collision do happen, then these grains produce fractures along their contact points. So, this is how the fractures are coming in the picture, that grains are rolling, and while they are rolling they are touching each other, and when they touch each other they produce fractures along their contact zones. And now these little tiny grains, they also contribute to the matrix, and therefore overall grain size reduces and the flow continues, and then the grains again do collide, further grain size reduces, and so on. So, this is the process of granular flow that we have learned, that what is the mechanism. Now, if you think of the examples, one of the recent devastating examples I can cite you, which you can see in this image, is the multiple cloud bursts that happened in June 2013 in Uttarakhand, India. What you see here in the middle standing the Kedarnath temple, and you can figure out these various boulders, pebbles and so on, sand size grains all over, they flew with the aid of water along this direction. Now, the water is gone and this is how it looks like. So, this is a classic example of granular flow. So, all these boulders, pebbles or sand size grains, when they are flowing with the aid of water, they rotated, they collided each other, they reduced their grain size and so on. Now, the same process do happen in a beach. When the waves do come, the sands, they just flow in this side, again they come back, flow again towards the beach side, again they flow towards the seaside. So, a continuous rolling is happening, and this is why if you are interested in sedimentology, you probably know that beach sands are very well sorted and they are also very rounded, and this is why and the mechanism of doing so is the granular flow. They continuously roll and they really become spherical or rounded. There is no sharp edge if you are sampling the beach sand or some sandstone with very nice roundness, then you probably can infer these are the beach sand deposits. Now, another example, this is also very recent in Kerala. Last year we had a significant flood there, and that flood was associated with a lot of landslides, devastating landslides. So, this is an image which I have collected from the Government of Kerala website, and this you can clearly figure out that this is one landslide. Okay. So, materials from the top flew towards this direction, they just rolled to this direction. So, this is a place near the government college in Munnar, Kerala, and that happened in September 2018. What do you see here, that these materials actually sort of just came down like sliding and rolling. So, this you can, a part of this flow can be described as debris flow, but again there is no confinement. The grains or boulders or pebbles, they were free to rotate, free to move, and while they were moving they actually did the job of granular flow. They contributed to the entire flow of this landslide. Now, we will look at the last one, that is the cataclastic deformation in the brittle field. Now, cataclastic deformation is very similar what we have learned with the localized deformation. Now, localized deformation do happen along a narrow zone, but cataclastic deformation do happen in a very large area, large scale, but the mechanism is more or less same. However, in cataclastic deformation, if you have to compare with the granular flow, cataclastic deformation do happen at or under very large confining pressure. So, it is a brittle fracturing of grains as it has to be, where you have to have some energy required to fracture the grains, which is less than the required energy to roll or slide. We will learn about it later. And then it is characterized, as I talked about, by high confining pressure and low fluid pressure. So, fluid is absent in this kind of deformation, or it is extremely low. And examples you can cite for this type of cataclastic deformations are brecciated rock or some related structures, fault zones, large fault zones, damage zones, and certainly impact craters. Now, before we go to the next slide on this illustration or similar illustrations we have seen with granular flow or localized flow. So, what happens, I just try to give you the difference or try to cite you the examples or cite you how does it work. So, in granular flow we have grains like this, which was filled by soft sediments, unlithified sediments and fluid. In cataclastic deformation we have grains under high confinement and less fluids. So, therefore, the grains are touching each other like this. So, this is granular flow and this is cataclastic flow. Now, if there is deformation, say for example, a shearing is happening in this way in both cases. Now, here the grains finds it easier to accommodate the deformation just by rolling, and while they roll they probably touch each other, they fracture, as we have seen in this image. So, in the previous slide. So, they can just fracture here and there, and this is how the grain size reduces. But in this case, this is exactly what is mentioned here, energy required to fracture the grains is less than the required energy to roll or slide. Because this is under significant confinement, the grains do find it is impossible to roll, because the frictional contact here, here, here and other places are extremely high. So, instead of rolling or sliding past other grains, the grains do prefer to sacrifice themselves by producing some sort of fractures along the contact zones. And when this happens, these fractures happen, they get again compacted, because there is no scope that porosity could stay there unless the grains themselves produce some sort of strong network or strong framework. Then again these tiny small grains try to rotate, but they cannot because of huge confinement. They again produce fracture, and this is how we achieve the cataclastic flow or cataclastic deformation. So, we see in the next illustration. What do we see here, these 4 illustrations. In A we have some compacted matrix, this dark grey and this greenish grains. Now, when the deformation comes in these sort of settings, which is highly compacted, lithified and it has significant confinement, then the grains cannot rotate. So, therefore, they produce fractures within themselves, and then these fractures are easier to either open or slide. Here in this grain you can see that you have some sort of sliding going on, you have some sort of opening going on here and so on. So, all these processes do happen, but what is important, you see by this fracturing the grain size got significantly reduced, and if that continues, what we finally achieve is, you see in the illustration D. So, the overall grain size reduces significantly. The grains, unlike the granular flow, are extremely angular. They are not circular grains or their edges are not rounded, they are extremely angular. So, this is one of the characteristics of cataclastic deformation, and if we see this kind of structures either in field or under microscope, these are known as breccia or brecciated rocks. So, we will see some examples now. Here is one very good microstructural study, scanning electron microscopy images, SEM images. So, this is the host rock, that is sort of undeformed rock. This grey areas are the grains and the black areas are your porosity. As you can see, when the deformation comes, then we produce some damages along the grains. So, you can see that these grains are getting fractured here, here, here heavily, like they are getting crushed, like someone hammered it. Okay. And then these grains do rotate by themselves, but they cannot. So, they produce further fractures and they got some sort of sorting. So, you have large grains here and here, which is filled by fine grained matrix. With further deformation, what we see that it is like a crushed mass where there is virtually no porosity. Now, you compare, this was your initial and this is your final. So, grain size reduction is something very important for cataclastic deformation. We will learn later that why the rocks do have to reduce their grain size to accommodate energy or to accommodate deformation. Now, the mechanism here, at least in cataclastic deformation, is extensive fracturing of the grains. So, rocks or the grains or crystals, they produce fractures within themselves, and therefore, the porosities and other things got reduced significantly, but it can happen in other ways as well. We will see it later. Now, here I try to give you some examples that when you look at look the thin sections under microscope, optical microscopes, you can have some sort of ideas that you are looking at cataclastic deformations. So, this is a single feldspar grain, as you can see here. And you can see this. So, these are the cleavages of these grains, you can figure out, and you can see this grain is characterized by some sort of fracturing here, 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 here and so on. So, these are characteristics of cataclastic deformation. In the next image, you can see that it is a microstructure of a small fracture in granite. So, you see that you have a very sharp boundary here and here, and in between you have lot of grains which are angular in nature, and you can also figure out that the grain size here on these two boundaries and the grain size in the middle are significantly different. You probably can see the fracturing processes going on. So, this was a large grain, and then you can see the fracturing is happening along this. So, this grain is divided in 3 equal pieces. Now, this is again a quartz grain, and I tell you it was probably a single crystal like this, and then it produced fractures here and here. So, this is also cataclastic deformation, and we see it in microscale. Now, the color of here and here are very similar, but here it is little different. So, you can ask that how do you say that this is a single grain, and this can happen that even a single grain after fracturing may show a different color, at least in this case the shades, and this is because the grains may have rotated. Therefore, we see within a single grain you see a different color because it has rotated, and therefore, its orientations got changed and we see a different color. This is you must have learned in your optical mineralogy lectures. Now, here are some other examples. So, this is a typical Brexia outcrop, and this is in Canada, and you can see this hat is the scale, and you see here this angular grains here, or these are not grains actually, these are clasts. So, and they are hosted within the fine grain matrix. So, this is an example of cataclastic deformation. Please note, this is not a localized deformation, because when you have an impact crater, a huge mass is impacting and then everything is getting fractured. So, it is not a localized feature, at least the scale we are thinking of. And this is another example, again it is from USA, from Death Valley, and you see this black things which are actually limestone clasts, and these are within the calcite cements which are white, and you see prolific angular clasts, and this is a very typical impact induced breccia. This is how it looks like, and this is an example of cataclastic deformation. Now, talking about this porosity reduction or permeability reduction, etc., particularly applicable for localized cataclastic deformation, here I try to give you a summary diagram, some sort of classification diagram. So, if I consider this one as an undeformed setting of grains, and this blue things behind are your pore spaces, then you can have pure compaction without any shear component. The rocks can deform, and then it can form the localized cataclastic deformation. On the other hand, you can have pure dilation, where rocks are experiencing uniaxial tension or something like that, and instead of uniform or homogeneous distribution of deformation, somewhere it just opens up, the grains produce fractures and you have an opening. So, clearly here this area is of low porosity and therefore, most likely of low permeability, but here it is essentially high porosity and low permeability. But if the shear comes in the picture, which is this one, which is simple shear, so it also produces something like that, where you reduce the porosity and permeability. Now, if compaction and simple shear they do combine together, then you have something called compactional shear, and if shear, simple shear and dilation they combine together, then what you get is dilational shear. So, these are the 5 end members, or I would say these 3 are the end members: pure compaction, pure dilation and simple shear, and any combination between them can happen. So, within the 3 end members you can have the localized deformation, localized cataclastic deformation, and based on the way the rocks are deforming, whether it is compaction, dilation or simple shear, the porosity and permeability of the rock would vary accordingly. Now, let us have some ideas or some basic concepts on the failure criteria, that what are the conditions when the rocks would produce fracture. As we have learnt that when we are discussing about this cataclastic deformation, that a fracture is produced when the shear strength is exceeded. So, during the brittle fracturing, therefore, the rocks can deform either by creating new fractures or can deform along a pre-existing fracture, and in both cases we have said about it quite a lot of time, the friction plays a very important role. So, the fracturing processes that involve friction, one can give or one can theorize it by Mohr-Coulomb failure criteria. Mohr-Coulomb failure criteria is expressed by a very simple equation, where shear stress or critical shear stress for fracturing is equated to S, which is the cohesion of the rock you are talking about. The mu is the frictional coefficient or coefficient of friction, sigma n is the normal stress, and Pf is the pore fluid pressure. So, eventually this sigma f minus p gives you the effective fluid pressure, or effective I am sorry, it gives you the effective normal stress. So, you can write it actually Tc equal to S plus mu sigma effective normal, which is equal to sigma normal minus pore fluid pressure. Now, we will discuss about these two terms, cohesion and friction, in the next slide, and in the slide after we will see that how does it work with the different rocks. But cohesion is something, if you have some sort of pre-existing fracturing in the rock, then there is no cohesion. I also tell you that this equation is one of the most important equations in brittle fracturing or brittle deformation, and extensively used in rock mechanics studies. And I repeat, this is known as Moore-Coulomb failure criteria. I also would like to remind you here that this is not a flow law, because what we have learnt in one of the previous lectures, that flow law takes care of three major parameters. One is the dynamic parameter, second is which is related to a kinematic parameter, and they are equaled or they are balanced by a constant, a rheological constant. Now, in this case, this is not such an equation. So, this is not a constitutive equation, but a law of failure or a criteria of failure, you can think of this way. Now, what is cohesion and what is friction? Now, we talk about these two terms very frequently. Now, cohesion is something, I just try to give you the feeling that when you have your material in rest, that is in static condition, there is no external force is being applied, then these particles can still stay together, and this ability of staying together of particles under static condition is cohesion. You can think of that the sands, the loose sands, if you make them, if you just set them somewhere, they lose and fall apart. So, the cohesion is low, but if you compact it by your hand and try to let it be there, it may stay for a while, but then it will fall. If you add little bit of water and compact it by your hand, it will stay for a while, and if you add cement and water, then it will stay for quite a long time. Note, there is no external force is being applied. So, in that case, the cohesion from loose sand to compacted sand to wet sand to the sand with cement, the cohesion is increasing. So, it is the ability to hold the particles together under static condition. Friction, on the other hand, if we try to understand physically, that it is a force that is developed between two adjacent particles due to application of stress. What I mean by this, that friction always requires, to define friction, it is always important to have an external source of force or stress, and when you have that, then these two grains would like to stick to each other, but because of this external force they cannot, or what is the resistance so that they can stick together is measured by a parameter which is known as friction. Now, in the previous equation we have seen that we wrote the equation in general, tau equal to cohesion plus mu multiplied by sigma n. This is this equation we have figured out. This is a Moore-Coulomb failure criteria. Now, the question is there any relationship between cohesion and friction? So, people performed experiments and they measured cohesive strength of different rocks. So, here we see a series of igneous rocks, here we see series of sedimentary rocks, and here we see series of common metamorphic rocks, and this is your cohesive strength, which is in the unit of which is megapascal. Now, this is lithic tuff, the cohesion is extremely low. For granitic rocks, these green ones, the cohesions are quite variable, and then limestones from very low to extremely high and so on. So, for different rocks, does not matter it is igneous, sedimentary or metamorphic, we see that the values are pretty distributed. If you look at the coefficient of friction mu, which is a dimensionless quantity, these are the same rocks, igneous, sedimentary and metamorphic, and we again see a various a wide distribution of this. Now, what we see here, which is very important message I would like to give you from this slide, that a rock is highly cohesive. That does not mean that its friction would be high, and vice versa is also true. For example, this lithic tuff, it has very low cohesive strength, but its frictional coefficient is quite significant. Similarly, schists, its cohesion is pretty wide, but its frictional coefficient is even less than the lithic tuff. So, cohesion and friction, they apparently do not have any relationship. However, this equation we would see now in the light of experiments and many rocks. What we can figure out from this slide is very famous plot from Byerlee, and this is known as Byerlee's law. So, Byerlee's law actually do describe the frictional strength for a wide variety of rocks under different loads, and then he tried to fit the data with two straight lines. So, how does it work? So, what he has done, he deformed the rocks, he measured the shear stress at different confinements. So, these are your normal stresses, the confinements, and then he calculated, or he from the stress strain curve, the peak stress. And there are number of rocks, variety of rocks he has used. I am not sure if you can read it, but from the slides, the PDF files I would give you, you can figure out. So, it has granite, fractured granite, ground surface, it has limestone, gabbro, dunite, sandstone, then different types of sandstone. So, faulted, saw-cut sandstones, granodiorite, gneiss and mylonite, then quartz monzonite with joints, then westerly granite, and a lot of clay minerals, and here as well. Now, we can see that interestingly all these values of shear stress versus normal stress, they more or less do follow a line. The first take home message from this plot is that the compositions is not a function of determining the frictional strength and the cohesion particularly. However, it is a function of normal stress. If we zoom this part, then we would see that here it is going through the center, and then this line, if we connect these lines, it is not going through the center, it is coming somewhere here. So, up to this around 200 megapascals confining pressure, Byerlee proposed that below 200 megapascals rocks hardly have any cohesion, and the slope gives the coefficient of friction. So, he got this equation that at low confinement rocks have coefficient of friction average 0.85. However, this is about 60 megapascal, this slope, if we continue doing like this. And here he found this equation that where the cohesion is about 60 megapascal and coefficient of friction is about 0.6. I am sorry, this is written wrong, this should be 0.6. So, this is how we can figure out that the friction or strength of the rock is not a function of the composition of the rock. Now, you can also figure out that there are some rocks or some minerals which do not agree with this plot, and these are these rocks. And if we see, these are mostly serpentinite, illite, kaolinite, halloysite, montmorillonite, vermiculite, and so on. Now, these do not agree on this plot of Byerlee's law, and they are some sort of outliers, and they are mostly clay minerals. It has a significant meaning that why they are outside and why studying of this sort of clay minerals are important, but we will not talk about this later, but I just tell you these are significant for earthquake studies. So, we finish this lecture and in the next lecture we will learn about intracrystalline plasticity. So, in this lecture we mostly have learned the cataclastic processes, where we mostly look at the grain scale processes, but without looking at the features that we have learned in the first lecture of deformation mechanism, this defects or dislocations or grain boundaries, because these things have no influence in cataclastic deformation, but they play a significant role in intracrystalline plasticity and dynamic recrystallization. So, this is what we are going to learn in the next lecture, lecture number 14.2. Thank you very much.